In this video, I'm going to derive the parallel axis theorem for the product of inertia. But you need to see where the parallel axis theorem comes from because we're going to use it for our composite shapes. We'll also use it a little bit when we talk about integration as well. It's similar to the product of the parallel axis theorem for moments of inertia, but with its own POI twist. So this is the picture. We have a XY axis. We have a general area. That area has a centroid at C. It has a set of centroidal axes, X prime and Y prime. There's a dA element on our area. Y prime is a distance from the X prime axis to dA. And there's an X prime distance from the Y prime axis to dA. I know we're using X prime and Y prime for everything. I apologize for that, but I think that's the way people do the derivation of this. dx is the distance from the y-axis to the y prime axis, and dy is the distance from the x-axis to the x prime axis. So the product of inertia of dA about the xy axes are x tilde times y tilde times dA. And so we've got dx plus x prime, and then we have dy plus y prime times dA. And if we integrate this guy over the entire area, then we have the integral of these guys. If we expand these terms out, we have a dx times a dy dA. We have an x prime times a y prime dA. We have a dx times a y prime dA. And we have a dy times a x prime dA. Since these are about the centroidal axes, and dx is constant, so it can be brought out of the integral. dy is constant, so it can be brought out of the integral. Since these are about centroidal axes, this integral of y dA is a moment equation about the centroidal axis. And again, half of that is positive, half of that is negative, and so the overall result is 0 because it's centroidal. The same is true with this guy. He is 0. And so you're left with a integral of x prime y prime dA, which is basically I bar x prime y prime. So in other words, I, the product of inertia, about the centroidal axes. And then the integral of dx dy dA. So the dx and dy are constant. They can be brought out. And so you have dx dy times the integral of dA, which is just area. And so finally, Ixy is equal to I bar xy, or I bar x prime y prime, plus area times dx dy. And this is the parallel axis theorem for the product of inertia. So in other words, if I have a composite shape, that's made up of sub-areas of rectangles, half circles, quarter circles, circles, triangles. If I can find their I bar, and I know their area, and I know their distance, dx and dy, then I can get Ixy for the composite shape by summing all of those up. And that's how we'll use it anyway, just like we did for moments of inertia. In a previous video, we derived the parallel axis theorem for the product of inertia. And soon we're going to apply the parallel axis theorem to determine the product of inertia for composite areas that are made up of sub-areas of common shapes like rectangles, quarter circles, half circles, things like that. But I wanted to take a few minutes in this video and just really carefully go through the Hibbeler crib sheet, what he gives, what he doesn't give, and to go through the crib sheet that I prepared and provided. And just to be sure you know the tools that you have to work with for common shapes. And also we're going to take some formulas of his, for example, and get the other one using the parallel axis theorem just for practice, just for exercise. Here's the crib sheet that I provided. It's in the OneDrive and also on the website. The top part are moment of inertia formulas, both I bar and I base. But the bottom part of the page is devoted to product of inertia. And so again, we just derived the parallel axis theorem for the product of inertia, for I about some set of axes. It should be IXY. So IXY about some set of axes is equal to I bar XY or I bar X prime Y prime about the centroidal axes of an area plus the area times dx times dy. So in order to use this, you need I bar values or centroidal values. Well, the good news for the parallel axis theorem for product of inertia is that the I bar for symmetric areas like a square, a rectangle, a circle, a half circle, a triangle that's symmetric, all of those I bars are zero. So some of these problems simplify somewhat because the I bar term is zero, and then you're just left with an A dx dy term. So those are simpler. On the other side of the coin, if you have right triangles or quarter circles, those are a bit harder because you have to pay attention to the orientation of the triangle or the half circle, quarter circle, I'm sorry. So these aren't quadrants, these are orientations. And so a quarter circle, the I bar, the centroidal IXY, is equal to 0.01647 r to the fourth. At this orientation, it's negative. At this orientation, it's positive. At this orientation, it's negative. At this orientation, it's positive. So you have to pay attention to the orientation on your problem. Not quadrant, but orientation. The same with right triangles. The I bars for these right triangles, the magnitude of them is 1/72, b squared times h squared. At this orientation here, the I bar is negative in quadrant one, or a quadrant one orientation. At this orientation, the shape is positive. At this orientation, the I bar is negative. At this orientation, the I bar is positive. So you just have to pay attention. Soon we're going to work some practice problems with these. So this is my crib sheet. This is what I provide. Let's look at the Hibbeler crib sheet. So the Hibbeler crib sheet, and which for S&T students, we often require you to use the Hibbeler crib sheet on exams. And so you have to understand what Hibbeler provides and what he doesn't provide. So if you look at his crib sheet, there's a rectangle, a right triangle, a quarter circle, and a half circle. And he gives an I bar, a centroidal I for this guy, which is zero, which you'd expect. He gives an IXY about the corner, what I call I origin formula, is 1/4 b squared h squared. We're going to derive that here in a moment. For this right triangle, he gives an I bar of 1/72 b squared h squared. Notice this is positive. He doesn't tell you, he doesn't give you the other orientations. He just says that's positive. Well, if you actually go back and look at my sheet, the triangle at that orientation is positive. If he turned that around, it would be negative. If you flip the mirror image vertically, it would be negative. So he doesn't give you the whole story there, but at that orientation, it is positive. And then he gives an I origin value with the x and y, which is 1/8 b squared h squared. And we're going to prove that here momentarily. Quarter circle, he gives the I origin value at x and y, but he doesn't give the centroidal value. The centroidal value, according to my sheet, let's look and see. So a quarter circle at that orientation should be negative about the centroid. It's positive about the x and y, but it's negative about the centroid. We'll prove that on another sheet. Finally, this is straightforward. He gives you an xy value, which is 0, and he gives you an I bar, x prime, y prime, which is 0, because this shape is symmetric about both of those axes, and so they're both 0. Let's actually work with those formulas on the Hibbeler sheet a little bit, just for fun. So for the rectangle, he gives Ixy is 1/4 b squared h squared. And of course, because this is symmetric, we know that I bar is 0. Well, let's prove this. So if we actually come down here, so given the I bar is 0 about the centroidal axis, let's find Ixy. So we'll apply the parallel axis theorem for product of inertia, and we'll say Ixy is equal to I bar x prime y prime plus a dx dy. I bar is 0. The area is b times h. The dx is b over 2, and the dy is h over 2. So we plug in a b over 2 and an h over 2. And so we're left with Ixy is 1/4 b squared times h squared. And that's what he gave here, 1/4 b squared h squared. So you should be able to get one of these from the other, either way. He gives you both, which is fine, but I'm just showing you how you could do that from the parallel axis theorem. Next, for this right triangle, he gives a centroidal value, which is positive 1/72 b squared h squared, and he gives an Ixy, which is 1/8 b squared h squared. Let's use the parallel axis theorem to prove this. So on the next page, we're going to accept the centroidal value, which is 1/72 b squared h squared, and we're going to find Ixy. So the centroidal value is positive 1/72 b squared h squared plus the area, which is 1/2 base times height. The dx distance is 2/3 b, because this is 1/3 b, this is 2/3 b. And then the dy distance is h over 3. So 2/3 b and h over 3. And so you're left with, so you can factor out a b squared h squared, and you're left with a 1/72 plus the 2's cancel, so you're left with 1/9. So 1/9, if you multiply that times 8 over 8, you get 8 over 72. 8 over 72 plus 1 over 72 is 9 over 72, which is 1/8. And so finally, we use the parallel axis theorem to prove that Ixy is 1/8 b squared h squared. And that's what he gave. So he basically gave the Ixy is 1/8 b squared h squared. And so you should be able to go back and forth between the two using the parallel axis theorem if you chose. Again, notice also that for this triangle at this orientation, he gave the I bar as a positive 1/72. If you look at my crib sheet, a triangle at that orientation is positive. But if that triangle was mirrored horizontally, it would be negative. If it was mirrored vertically, it would be negative. And so he doesn't give you those other orientations. I think you should know that. That's why I provide it, because I just think for completeness, I think you should know it. Finally, let's look at the quarter circle. So the quarter circle, Hibbeler gives the IXY value, but he doesn't give the I bar. So let's use the parallel axis theorem to get the I bar. So the parallel axis theorem says IXY is equal to I bar x prime y prime plus a dx dy. In other words, the I bar is equal to IXY minus a dx dy. The IXY he gave is 1/8, 1/8, r to the fourth, and then minus the area of a quarter circle, which is pi r squared, oops, that's squared, pi r squared divided by 4. And the dx is 4r over 3 pi, and the dy is 4r over 3 pi. The 4's cancel, 2 of the pi's cancel, and so you're left with 4 over 9 pi. And of course, we factored out an r to the fourth. There's an r to the fourth here, and then r squared times r, which is r to the fourth. So 1/8 minus 4 over 9 pi is negative 0.01647 r to the fourth. He doesn't give that to you. He just gives you the IXY. And so if you look at my crib sheet, I basically gave you the 4 different orientations of a quarter circle. And a quarter circle at this orientation has a negative sign. If it was mirror imaged around the Y, it would have a positive sign, and so forth. So you have to pay attention to the orientation of the quarter circle. Now, don't be confused. Earlier, we talked about a shape in quadrant 1 or quadrant 2 or quadrant 3 or quadrant 4. These shapes are not in quadrant 1, 2, or 3. This is just an orientation. This isn't a quadrant. So it's a subtle difference, but it's a difference. So again, this exercise just builds your muscles in terms of using the parallel axis theorem. It also familiarizes us with my formulas on my crib sheet and also Hibbeler's formulas on his crib sheet. So you know the pieces that you have to work with when we get to composite area problems. One more crib sheet I'll show you, your set of formulas, is this sheet. And this sheet repeats what we already know. So it repeats a product of inertia here. It repeats that our IXY for symmetric shapes are 0. It gives us our right triangle formulas at different orientations, which we saw. It gives our quarter circle values at different orientations, which you've seen. But one new thing it gives is it gives the at origin equations. And so if you happen to have a rectangle at an origin, or a quarter circle at an origin, or a right triangle at an origin, either one orientation of a right triangle or another, then you can use these formulas directly without using the parallel axis theorem. And so for rectangles, the quantity or the magnitude is 1/4 b squared h squared. It's positive if it's in this corner. It's negative if it's in this corner, positive and negative. So this is a rectangle at the origin. Hibbeler gives that formula. A quarter circle at this origin, positive 1/8 r to the fourth. Hibbeler gives this one. At this orientation, it's negative. At this in this quadrant, it's positive. This quadrant, it's negative. If it's at the origin. Hibbeler gives this triangle right here at the origin. He gives it as 1/8 b squared h squared. But that same triangle in quadrant 2 is negative. Quadrant 3 is positive. Quadrant 4 is negative. And again, these are for right triangles with its point at the origin. Finally, if you have a right corner, a right triangle whose right angled corner is at the origin, then the IXY is 0.04167 b squared h squared, and it's positive if it's in this corner, negative if it's in this corner, positive here or negative there. And I call those at origin formulas, which are unique to product of inertia areas because it's with respect to two different axes. Remember, for Ix or Iy, those are with respect to a single axis. So for those, we have an I base form, but for Ixy, we have an I origin form, or you might say an I corner form. So that's relative to two axes, not one. So that concludes this video. Again, just building our muscles, working with product of inertia, familiarizing ourselves with the crib sheet so we can work problems for composite areas.